Okay, so I wanted to continue on with this overview of different types of quantum chemistry methods. Um, I'll just briefly mention a flavor of techniques called Symmetry Adapted Perturbation Theory techniques. And so this uses perturbation theory, but it uses perturbation theory in a slightly different way than you might imagine based on how we've discussed the electron correlation problem. So there are perturbative techniques where the perturbation is essentially building in the explicit electron-electron correlation that's missing from Hartree-Fock. But symmetry-adapted perturbation theory is a bit different. So it is really meant to capture intermolecular interactions. So this would be interactions between different molecules. And so the perturbations are different interaction components which can be classified into these sort of physically intuitive components like electrostatics, dispersion, induction polarization, and exchange repulsion. And so you can get sort of a flavor of symmetry adapted perturbation theory, which is called SAPT 0, that gives you kind of a qualitative description of these intermolecular forces, but you can improve upon this using higher order perturbation theory in these intermolecular interactions, and these lead up to this technique SAPT 2 plus 3, and this is more expensive, so this is 7th order scaling, whereas SAPT 0 is 5th order scaling, but this starts to give you quantitative description about these intermolecular interactions. So anyway, so that's just something that I wanted to point out. So when would you might do this? So if you have different molecules, and this is an example just of these different base pairs of nucleotides, and you want to get their interaction energies. And so, for example, these base pairs have these hydrogen bonding interactions and other kinds of intermolecular interactions. So these are really chemically distinct entities, right? You've got a molecule over here, and you've got a molecule over here, and they're interacting through hydrogen bonding, which we think of as sort of an intermolecular interaction, not an intramolecular interaction. And this can be captured through SAPT. Additionally, if you stack different molecules in different configurations, they may have all different kinds of interactions between the molecules that are not intramolecular, and these can be captured with SAPT. So that's a really interesting flavor of techniques. It's not really relevant for the things that we are looking at in our class, but I just wanted to mention them. Okay, so I think this is going to be a topic of one of the team's technical presentations, but an alternative approach, which has a lot in common with configuration interaction, but is different in a very important way, are called couple cluster methods. And so sort of at the heart of couple cluster methods are the following two ingredients. One, you're going to write sort of your wave function model as this exponential ansatz of the reference wave function. And so when you think back to our discussion on unitary transformations, right, this is actually very similar in spirit. This is like an operator which applies a transformation to the reference wave function. The difference, though, is that T hat is not an anti-Hermitian operator, so this is not a unitary operator, but this is an example of a transformation called a similarity transformation. So it has a lot in common with unitary transformations, but not exactly identical. But nevertheless, and when you end up applying these transformations to operators, like if I think about having the Hamiltonian operator, and then the bra is this transformation on the reference state, that the ket is this transformation on the reference ket, and then the bra would be the conjugate of this transformation on the reference bra. I can think of that as as a similarity transformation of the Hamiltonian, which obeys this BCH expansion, just like our unitary transformation of the operators did. Okay, just wanted to point that out. But this T-hat operator, what it is it's a sum of excitation operators. And so if I were to just directly apply this T-hat to a reference ket, right, in a linear way, I would get configuration interaction theory. So the difference is I'm exponentiating t hat, and so that means I have basically an expansion in different powers of t hat, because you can expand an exponential of anything as this power series expansion, right? And so what that ends up meaning is that the exponentiation of t hat will end up with sort of the application of different powers of the sum of whatever excitation contributions there are, okay? And so a typical thing to do, right, is I could say t hat in principle should include all the way up to n order excitations, where n is the number of electrons. But then, as I've seen in configuration interaction, that gives me this gigantic space of determinants to work in. And so what I typically do is I will truncate at some smaller order of excitations, typically at T2, which includes doubles excitations. So then what you end up with is an exponentiation of T1 plus T2, and the difference is that that power series expansion will give you pure T1 and pure T2 terms, but it will also give you terms that have products of T1 with T2 and T1 squared and T2 squared and things like this. So you effectively have sort of higher order excitations that are included in this exponential ansatz of the t-hat operator. And so that has some advantages. There's some very technical advantages to the types of excitations that are actually retained in this expansion. And I won't go into detail because I think that's something that the technical presentation will touch upon. But one of the properties that arises is that couple cluster truncated, even at finite orders of excitation, will be size extensive. And that's not true of configuration interaction with truncated excitations, okay? So now, one of the things is that oftentimes people will use a technique called couple cluster singles doubles with perturbative triples, that's CCSD parenthesis T, right? This is known as the gold standard method in quantum chemistry. It's typically, quantitatively accurate, at least near equilibrium geometries. We've already seen that it can fail far from equilibrium if you've tried this on your HF stretched away from equilibrium. But the idea here is that the cluster operator, this t-hat operator, is going to contain T1 and T2. And then we're going to use perturbation theory to approximate the contributions of T3. That's why there's a parenthesis T. So it's not exactly including the triples, but it's approximating the contribution of triples. If you want to exactly include triples, then that acronym would be CCSD-T with no parentheses. And then if you included quadruples, that would be the T4 cluster operator, right? I would have CCSD-TQ and so on. All right. All right, so the last thing that I want to talk about is density functional theory. So density functional theory has a very different philosophy than what we've been talking about so far, because the central object in density functional theory is not a wave function. It's actually the electron density. And so the challenge, right, what is the challenge of density functional theory is that we don't know exactly how to relate the density to the energy. But here's the idea, right? I have this quantity called the electron density. So what is it, right? It's just some function of one electron coordinate, r. So this is a three-dimensional object, right? X, Y, and Z coordinates, for example, or r, theta, and phi, however you want to express this coordinate. And I have a density at every point in space. But that's it. So this is dimensionally a much smaller object than the wave function, right? It scales with, it is it has basically 3 degrees of freedom rather than n to the 3 rather than 3 times n degrees of freedom. All right. And so there is this theorem, the Hohenberg-Kohn theorem, which says that the external potential with a unique functional of the density can reproduce the ground state energy exactly. Okay, so what is this external potential? This would be like the Coulomb attraction between the electrons and the nuclei, and then this functional, right, of the density is what's encoding the electron interaction. So exchange interaction and correlation interaction. And so the problem is we don't know what that functional is. Okay, but in principle it exists, and so it can allow us to map the density to the energy. So part of what density functional theory does then is tries to come up with good approximations to that functional to map the electron density to the energy and allow you to sort of optimize electron density using the variational principle. In other words, minimize the energy through the density using the variational principle. Okay, so there's lots of different formulations. So these acronyms like B3LIP, PBE0, B97, MO6, 2X, etc. Right? These are all names of functionals, which are approximate mappings from the density to the energy. And none of them are exact. They are all approximate. Okay, so no one knows the exact mapping. So why are they used if no one knows? Well, sometimes they're really good. And also, because they are dealing with the electron density, they are rather than the wave function, they don't have this really challenging scaling with the number of electrons. So in principle, right, this actually could just scale linearly with the system size, but if you use a Gaussian basis set, essentially you have to do something like Hartree-Fock to optimize the density. So in Gaussian basis sets, basically density functional theory methods scale as n to the fourth, where n is the number of basis sets. But actually you can formulate density functional theory on a real space grid, in which case this scaling is linear, or can be made linear if you really try hard. Okay, so those are the good things. It's really cheap, so we can do really big systems with density functional theory. So even with Gaussian basis sets, we can do huge systems because the scaling is like Hartree-Fock, but it is often much, much better than Hartree-Fock, but sometimes it is not. So density functional theory can fail in a number of really simple cases, and density functional theory cannot really be systematically improved in the way that wave function methods can. And also there are many, many choices of density functionals. So this is a list of density functionals offered by a quantum chemistry package called QChem. I also would encourage you, since we've been using Sci4, to go to Sci4's page and figure out how many different density functionals are available in Sci4. It's a huge number, right? So these are options for different density functionals. And how do you choose the right one? Well, what does QChem say? Please consult the literature to guide your selection. Okay, so in other words, which one of these is the best? Well, we don't know, right? Read the literature, because for different contexts, different functionals will perform better. Okay, so what can we say about, sorry, let me skip ahead. What can we say, right, about improving on density functionals? So it's quite difficult to sort of say we can systematically improve density functional theories by adding particular kinds of things, but there is sort of this guide, the so-called Jacob's ladder of density functional approximations, with this sort of hierarchy of approximations that can be built in, okay? And the lowest rung on this ladder is called the local density approximation. So that essentially means that your functional is going to be using strictly information about the density of the electrons in a particular point in space, right? So really the information about rho of r is what goes into the density functional to get the energy. Okay, the generalized gradient approximation is going to, in addition to having just the density itself, it's going to be looking at how the density is changing as a function of r. So this is the gradient of the density. Right, the first derivative of the density with respect to r. That's this GGA approach, so generalized gradient approximation. We have higher than that, this meta GGA, and so that has all of basically the gradient of the density plus the Hessian, so that's the second derivative of the density with respect to displacement along the coordinate. And in addition, it builds in information about the kinetic energy density. Hyper-GGA includes some exact Hartree-Fock exchange. So there is, in Hartree-Fock theory, a type of electron-electron correlation that has to do with the exchange of same spin electron coordinates. And so Hartree-Fock actually captures the exact behavior of that kind of correlation. It essentially has arises from the anti-symmetry of the Hartree-Fock wave function, which creates these kinds of holes called Fermi holes, which are regions of space where two same spin electrons cannot simultaneously occupy. Okay, so Hartree-Fock actually captures that exactly, and it's quite difficult to build these density functionals that captures that exactly. So some way people have come up with to include some of the features of this Hartree-Fock exchange into their density functional theory. And then beyond that, what can we do? Well, you can start doing perturbation theory on top of density functional theory to build in features that you were missing from density functional theory. So this is sort of the ladder. And each of these is going to be sort of more computationally intensive than the lower rung, and in principle better, but maybe not always. Okay. So anyway, these functionals, right? These are some complicated functionals of the electron density. Let me just briefly remind you, if we haven't already talked about this nomenclature of a functional yet. So a functional is like a function, except for it maps another function to a number. So you could ask the question, well, what is a function? Sort of fundamentally, a function is something that maps one number to a different number. And you can think about like f of x is equal to x squared. Well, then that function f of x is a map between a number and the square of that number. Okay, so a functional, on the other hand, instead of feeding the functional a number, you feed the functional a function, and it maps that function to a number. And so if you think about what like our expectation values, our energy expectation value computations do, right? They basically take one function, right, the wave function, and they act on that function with the Hamiltonian, right? They project the result of that onto the complex conjugate of that function, and then they integrate over all space. At the end of that operation, you get a number. So you feed the expectation value a function, and you get a number out. And so that's sort of the idea of what a functional is. It's very similar in spirit. The only difference is that, unlike with an expectation value of the energy that we normally think of, where you feed it a wave function, in this case, you're going to feed it a density function. right? And that is a sort of simpler object, generally speaking, than the wave function. But nevertheless, there's going to be some operations and some integration over all space, and then at the end of the day, you're going to get a number which represents the energy. Okay, so picking or defining a density functional is going to sort of define sort of the recipe that you take your density function through in order to map it to a single number, which is the energy. And so once you have this recipe, right, you can sort of tune, sort of the amounts of each little ingredient in the recipe, or parameterize it in order to improve it against some metric. So sometimes that's empirical data. Sometimes it is computations with, for example, coupled cluster singles, doubles, and perturbative triples, or perhaps even full CI if you can afford it. But you can sort of tune your functional to match some data set, okay, which basically will improve the accuracy of your functional for some specific context, although it doesn't often apply broadly speaking, right? It typically will perform well for the context that you've optimized it for, and you don't know beyond that sort of training set how well it does. Very much the same case for things like machine learning. Okay. So this is just sort of a workflow of that concept of building a functional, right? You essentially want to think about minimizing some, measure of the error over a lot of different systems that you have applied it to. Okay. So anyway, last couple of things I'll say is that sometimes these density functional theories can give you really reasonable results, and sometimes they don't. So these are just some errors for different density functional theories compared to a composite of different wave function methods. So these wave function methods will summarize the accuracy from these levels of theory, including Hartree-Fock, second-order perturbation theory, fourth-order perturbation theory, and CI singles doubles with perturbative triples, and these Q corrections, sort of. So this is some approximation to CI singles, doubles, triples, and quadruples, but it's not exactly that. So anyway, these are considered, reliable benchmark, and you can see, some functionals. For example, this LSDA, has an average error, which is like 35 times greater on one metric, which is atomization energies, but it's only 6 times greater on ionization potentials, only 5 times greater on proton affinities. Overall, this functional LSDA is not that great for this data set. This functional, on the other hand, B3PW91, has sort of twice the error on atomization energies, about 4 times the error on ionization potentials, but almost the same error on proton affinities, right? And so it's kind of all across the board. And so that's sort of what is meant by you need to consult the literature, right? So you should ask yourself, sort of like, what is the chemical context that I'm trying to model? Meaning, like, what kind of molecules do I have? Do they have metals in them? Are they only organic? Do they only have first and second row atoms? Do they have third row atoms, right? Like, how have these methods performed on those classes of molecules in the past? Second question is, what properties do I care about? How have these functionals performed on these properties, right? So these are both important considerations when picking density functional theory, all right? So again, this very common functional is B3-lip. It's sort of like if you're, an experimentalist looking to do some calculations, like often B3-lip and 631G star is where you start. And part of the reason for that is that, sort of broadly speaking, over test sets on lots of properties, reaction energies, enthalpies of formation, ionization potentials, electron affinities, proton affinities, B3-lip does pretty well. Okay, That doesn't mean it's going to be accurate for your specific context, but what it means is that your chances of accuracy are relatively higher with that functional than with other functionals with no additional information. All right, so not necessarily advocacy for B3-LIP as a blind choice, but you can see why people go to it, because on average, on a fairly comprehensive test set, it has the smallest average error. Okay. So some caveats, right? B3 density functional theory can be really good, can also be really bad. You should be very careful. So that's it. All right. And there are many known challenges with DFT, and hopefully I have captured this. This is an interesting peculiarity. It has the self-interaction error. So these are, this is an energy expression which is common to both density functional theory and Hartree-Fock theory, but the difference is that in Hartree-Fock theory, this Coulomb and exchange operator will exactly cancel each other out when, in the cases when I have electron index 1 and electron index 2, so I and J are the same. In density functional theory, the exchange is different than in Hartree-Fock, so these terms do not cancel each other exactly. So what does this mean? There is some non-zero repulsion between an electron with itself, right? When this term disappears in Hartree-Fock theory, it's basically saying that when these two indices refer to the same electron, there is no interaction between that electron and itself, right? But DFT, this term doesn't vanish. There is some self-interaction, and so you can see this cropping up, for example, in this bond stretch for H2 plus, right, which is a system which has exactly one electron. And so there is error that becomes particularly pronounced at these stretched bond lengths through B3-LIP because of this self-interaction energy error. So that's just one other very peculiar feature of density functional theory, where Hartree-Fock theory, which would be exact in this case, does not have that problem, and wave function methods will not have this problem. All right, so that's all I'm going to say, and I hope this was helpful.